Welcome back to ECE 441A, 541A. Homework number 3 is upon us. It's after the weekend. It's Monday, the 8th, that it's due. The second exam is coming up pretty soon. That's in a little more than 2 weeks. And lab number 2, everything is happening soon, isn't it? So hopefully I will have a chance to look at those over the weekend and provide corrections if necessary for your plant. In lab number 1, you were actually looking at injecting some command here U and measuring some output Y. And one of your big objectives was to get G, to find G of S. Case of PF, you specified. That was 0.15 or 0.075 or something. That was a gain, a fixed gain in your lab number 1. We factored that out so that we had G of S remaining, and now in lab number 2, what we want to do is not do an open loop scenario, but do a closed loop. We want to close the loop. This is an open loop scenario. We inject something and we see what happens. We really have no way of manipulating the output other than through the adjustment of the gain, case of PF. In lab number 2, what we want to do is change the dynamic behavior. If you weren't happy with the way your system was shaking, lab number 2 will hopefully improve upon that. And that's really chapter 5 material. How do you place the poles of your closed loop system using feedback? And we will actually use more than just a single feedback signal. We will actually use 2 signals, position and velocity of that mass, and weight those independently to have somewhat arbitrary selection in where we locate our poles in that closed loop system. That's lab number 2, and maybe we'll open that up and you can start on that next week, is the plan. That's not due for a while. It's basically due a week after exam number 2, but exam number 2 will cover the contents of lab number 2, just like exam 1 incorporated lab number 1 material. Today what I want to do is talk about trade-offs. Control is full of trade-offs. That's what control is about. But here we are going to be trading off or examining the sensitivity function, S, and the complementary sensitivity function, C. And hopefully in today's presentation or material, you'll see why S, if that's the sensitivity function, why we're calling C the complementary sensitivity function. They complement each other, or they go together in a certain way, and that way then forces one to influence the other. We'll then pick up actually after what we left off before. If you were looking at the notes from last time, there are some AC notes that were added, some after-class notes. We were looking at finding the sensitivity of an open loop versus a closed loop scenario. After class, I looked at the closed loop sensitivity, and hopefully that you can see is different than 1, which is what we derived last time for the open loop sensitivity. Meaning, the open loop sensitivity said if we had a small change in the plant, that small change was exactly what the transfer function experienced. In the closed loop, we could adjust that using feedback. We'll then work through that same scenario, sensitivity scenario, using a different formula or a different expression, and we'll start seeing that that sensitivity expression is a function of frequency. And how do we view frequency domain expressions? A lot of times we look at their Bode plot. And so you'll want to start thinking about, how do I start in rough terms sketching a Bode plot? You can have MATLAB do it very precisely for you, but you need to be able to check MATLAB's work for accuracy. And then the next part of this semester, we will move into Chapter 5, which maybe will be today. Probably it will be the next time we meet. But Chapter 5 is what Lab number 2 is based on, and that is how do you achieve particular performance out of a system? How do you meet design specifications? As I indicated in the intro, control is full of trade-offs, and the trade-off that we are going to talk about today is the trade-off between the sensitivity function S and the complementary sensitivity function C. How do we decide how we play with those? Another trade-off that we will have coming up now is performance. We can maybe adjust the performance of our system to be really great, but then its steady state accuracy might not be so great. There's a trade-off between what's happening with the system's accuracy and steady state and how its transient system behavior performs. What we want to do now is look at this concept of feedback, and I've tried to color code this in some intuitive way, or maybe it might help. The signals that are driving this system are indicated in red. We have our normal reference input signal, that's on the left, but then we have two other input sources. One is a disturbance, that's T sub D, coming in between the controller and the plant, and the other input is a noise. That could be measurement noise. That we measure something and there's actually noise in that measurement. How do we deal with that? Or what do we need to concern ourselves with if we have an input at N? And what we may want to do now is find out what the output is, Y of S, relative to all of those inputs, R, T sub D, and N. What was a disturbance we talked about last time in our class? Does anyone remember? Maybe it wasn't in the class, but it was in the lead-up or discussion of homework, whatever homework you're working on, number 3. Do you remember what disturbance we talked about there? Think about what's in the sky. If you're trying to collect solar energy, we talked about one disturbance being clouds going across and maybe influencing our system behavior. Another disturbance, I'm sure most of you have flown, but when you're in the air, sometimes you have turbulence. That's a disturbance. That's something that wasn't necessarily planned, but it does act like an input into the system. And now how do you correct for or respond to those disturbances? If you're driving and you set the cruise control, now you experience a hill or some other slope change, that's a disturbance. There's all types of disturbances that can play into this dynamical system behavior, and we may want to design our controller such that we can minimize the impact of that disturbance on the output. The plant is usually given. If you are in the early stages of design or development and somebody says, oh, how do we build this plant? Knowing what your control knowledge provides you, it might be to your advantage to get into that process early and help with the design of G of S so that your control task is not as difficult. But typically we're just handed, or we have to work with what we're given. The G might be fixed, the plant might be fixed, and now what do we have? We have the controller to manipulate. We can now adjust G sub C. Here are just the different labels. R is the reference input, N is the measurement noise, and T sub D is our disturbance. But I want to draw your attention to something that you might gloss over if you're quickly reading through this material. And that is the difference between that signal E sub A coming out of the summing junction and E that I've now highlighted in red. They are not the same. E is the tracking error. That's the difference between the reference input and the output. But what's E sub A? Well, E sub A is not just R minus Y. There's some other junk between Y and E sub A. If you're now trying to find that tracking error, you won't find it in your block diagram. It doesn't exist. You have to create it or build it with just some equations. But we will be focused maybe on the tracking error versus that signal E sub A. E sub A has this noisy output that's maybe filtered through the sensor. Typically, though, in this discussion, we're going to fix the sensor to just be a 1 or a unity gain. We'll assume our sensor dynamics are perfect or ideal. We don't have any sensor dynamics. I tried to then convince you that E sub A is not equal to E of S, and that E of S is not a signal in that physical configuration. You can't find a signal in that block diagram that corresponds directly to E of S. One more variable that we will be using today is this new transfer function, capital L of S, called the loop gain. And that's the product of all of those transfer functions in the loop, G sub C, G, and H. And in this, to simplify things, we're just going to go along with the textbook and assume that H is equal to 1. And when I now say the loop gain, that's probably going to refer to G bar, where G bar now is the product of the controller transfer function and the plant. So when I say the loop gain, you can think about that cascade combination in the block diagram of the controller and the plant. That's the loop gain. And I'm assuming that you've already all derived this equation based on that block diagram. I think that's why you were all just frantically writing things down as I was talking. You were deriving this expression. This is actually equation 4.4 in the textbook, but this now tells us how the tracking error is influenced by the three different inputs in our system. The reference input R, the disturbance T sub D, and the noise N. I've also identified, in addition to L and G in those transfer functions, I've now labeled the first one, 1 over 1 plus L, as S. That's the sensitivity function. And the third term on, or the farthest term on the right, L over 1 plus L, that's the complementary sensitivity function, C. We're going to derive that. But how would you derive this from this block diagram? Where is E in that block diagram? I covered up the answer, didn't I? It's not there. E is not in that block diagram, but what can you find from that block diagram relative to all of your inputs? You can find Y, can you not? You could use block diagram algebra and keep track of all the three inputs all at once and try to find an expression for y and then subtract that from r to obtain e. But what's another way of approaching that problem? This is a linear, time-invariant system. It's linear is the main thing. If it's linear, superposition holds. If superposition holds, that means we can find the transfer function between each of those individual inputs independently and then sum them all up at the end. And that might clear up your thinking or the analysis if you simply zero out two of the inputs and find the transfer function between one and the output y at one time. And do that 3 different times. Once for the reference input, once for the disturbance input, and once for the noise. Let's do that for the transfer function between the disturbance and the output y. Does everybody see what we're trying to do? We're trying to find this expression E, or formula for E, the tracking error. It doesn't exist in the block diagram explicitly, but we can find the output y. And R is just a signal. And now what we are doing is we said, oh, if we are playing with a linear system, we can now use superposition and Mason's gain 3 different times to try to find the 3 pieces that make up the expression for eventually E. But for now, let's just find the 3 pieces that make up the expression for the output y. So let's find the transfer function between t sub d, viewed as an input, and y, the output. And what are we doing with the other inputs? We're zeroing those out for this particular part of the analysis. We're going to use superposition. So now let's find this transfer function between t sub d, the disturbance input, and the output y from the block diagram. Is it clear what I'm wanting you to do? Now I want you to go to this block diagram and find the transfer function between here and there. And I hope that you know that it's not G, because you have all of this interconnection. But we are assuming this is gone and that's gone for this first piece. We don't have to worry about R, we don't have to worry about N in finding this first transfer function between t sub d and y. And now I'm going to force your hand. I'm going to say find this transfer function using Mason's gain. Because on exam 2, you might have to just be second nature using Mason's gain to find transfer functions, and then you have to do sensitivity once you found the transfer function. So how do we apply Mason's gain to find this transfer function between t sub d, the disturbance, and the output y? What do we need from Mason's gain? How do I get from here back to ECE? Do I follow a path? We need to worry about paths and what? Hopefully I won't just keep looping, although if you would just follow me from Monday and Wednesday, eventually I do loop back here, but I probably cross myself, don't I? So that's not a loop. We need paths and loops for Mason's gain. What's the path from t sub d to y? This is difficult. G. Right? That's the path. What's the loop? Or loops? That's not too hard either, is it? Just remember to keep track of the minus sign. That's just G sub C, G times H. Are we clear about paths and loops? And what happens, I'm going to scroll beyond this, what happens now if I want to find cofactor for that path? What's the process involved in finding the cofactor for a path? You virtually erase that path and see what loops were disconnected and remove those disconnected loops from your determinant expression. And boom, we have the cofactor. We only have one loop, we only have one path, we have one cofactor to play with. So let's now put all of these pieces together. Again, we're trying to eventually arrive at this expression, equation 4.4. And now we're working at the transfer function between t sub d and y. The path between t sub d and y you just told me was g. The loop was minus g sub c g h. And we're going to just go ahead and let that be 1 for using the textbook notation. This is now going to be minus g sub c g. Now, what's the determinant expression? Have to do all of these different products. Really? For this? How many loops do I have? 1. So I don't even have a pair. I just have 1 minus L. I don't need to worry about pairs of products. I don't even have multiple loops. This is now going to be 1 plus g sub c g. Or I'm going to call that g sub c g, as I indicated before, L, the loop gain. And what's cofactor 1? You already told me that if you eliminate that path from t sub d to y, that disconnects the only loop we had. Our cofactor is now 1. Now we can put all of those pieces together to find the transfer function between t sub d and y. That's the notation that I'm using. T sub d to y, that transfer function, that's now p of y t sub d times delta 1 over delta. And p sub y t sub d was just g. Delta 1 was 1. And there we have it. There's our transfer function between the disturbance, t sub d, and the output y. Questions on where that came from? Stop. I know you're all frantically deriving the other 3, but just be patient. Do those at home tonight, okay? I'll give you the answers. Here are the answers in the back of the book. Examine this after class. The transfer function between r and y and the transfer function between n and y. You can now verify those. And I know you're all going to do that and send me emails to that effect. Then what happens? You take those 3 transfer functions, and by superposition, you can create the y. And y is just now this sum of 3 terms between the reference input r, the disturbance input t sub d, and the noise n. And from that, we can subtract y from E and end up with this equation. That's equation 4.4. With S, what was S? Wasn't the stop sign. Is everybody clear on what's going to happen later this morning? In your next, no, not the next class, but the class after, a little after 11, your phone's going to go crazy. You're going to get an emergency alert. Just letting you know, if something starts going crazy in your phone, it's a national emergency alert. It's a test of the emergency wireless broadcasting system. Nationally. So you can play a role in this national experiment. I don't even think you can turn it off unless your phone is off. Then maybe your instructor at the 11 o'clock hour will say, everybody turn your phones off before we begin class. I didn't have to do that today. Oh, where was I? Oh, that was our stop. That was the stop sign. No, S is the sensitivity function, isn't it? What's C? Complementary sensitivity function. And that's what I'm telling you here. You can find that in the text. S is 1 over 1 plus L. L is the loop gain. If we assume H is 1, the loop gain is just the product of the controller and the plant, G sub C and G. There's our sensitivity function. Complementary sensitivity function, try to say that fast. Well, I'm curious what that sounds like at triple speed, which is what people listen to this at, apparently. C is now L over 1 plus L. What happens if we combine S and C? What if we add them up? Well, we already have a common denominator. What's the numerator? It's the same as the denominator. Now do you see why C is called the complementary sensitivity function? If S is 1 over 1 plus L, they complement each other. They go hand in hand. Their sum equals 1. And that now gives us a trade-off. What happens if we said, well, I want to reduce the sensitivity in my expression or in my system? If I decrease S, what happens to C? Does it go down? It can't, can it? This is like a waterbed where the normal is 1 and you push something down, the other one goes up. So S and C have this complementary characteristic or behavior. If we decrease S, we are actually going to increase C. So if we come back here to the air signal and somebody says, oh, I want to reduce the air between the reference input R and the air, I want to reduce S, well, what's that going to do to the impact of the noise on the air? It's going to make the noise worse in that particular location. And why do I say location? What is S? S is a transfer function. It depends on frequency. So maybe we can adjust S in certain frequencies of interest to minimize it when R is important. And maybe we could then minimize it in a different frequency range, or minimize C in a different frequency range when the noise is important. Hopefully R, the reference input, and the noise aren't in the same frequency ranges. Maybe, if we're lucky. So we can sometimes, relative to this loop gain, we can make G sub C large. That's what we can control. That's our controller. Now I'm hoping you're just seeing these Bode plots. If G sub C is the transfer function of your controller, making it large at small frequencies and then making it small at high frequencies, do you sort of see this Bode plot behavior of G sub C? That might have the impact that you want relative to this trade-off between S and C. And that's just a restatement of what I illustrated a minute ago, is that E, the tracking error, depends on those three through three different transfer functions, and we have to now make this trade-off. We have to figure out how do we adjust our controller, G sub C, such that each of those three transfer functions behave properly at the appropriate frequency or in the appropriate frequency band. What have we learned? Do I want to have you answer that? Have we learned anything this morning? What have we talked about? The generic topic was feedback. That block diagram with all of these different signals, trade-offs. We need to figure out, okay, if that's important, how do we now compute sensitivities? How do we create this sensitivity expression? And how do we compute it? Because you're going to have to do this on the exam. Suppose I now give you the following system. Suppose we have a controller that's K over S plus alpha. That's a first order single pole controller. I'm assuming we now maybe have the ability to adjust the pole location, the alpha, and maybe we can adjust the gain K. Could you build this out of some op amps and some R's and C's? You should be able to. Now you have this controller, and you can be able to adjust the K and the alpha. And suppose that you're applying that to a plant that looks like 1 over S plus 1. What would you say about that plant? What could you tell me about that plant? If somebody put that in front of you on an interview and said, tell me what you can tell me about 1 over S plus 1. You have a pole. Where is that pole? -1. Is that a good location? Is it an okay location? It's stable, isn't it? It's in the left half plane. It would have a mode corresponding to e to the minus t. What's the time constant, open loop, of that plant or system? What's tau? What would make that exponent, what time would make that exponent be 1? Forgetting the negative sign. 1. So after 5 seconds, what's infinity? Infinity is 5 seconds in this case for the open loop. We're now adjusting that through this controller. And we maybe want to know how sensitive is this closed loop system to us changing alpha, the pole location. So let's now build this into a closed loop system. And we will use negative unity output feedback. And now we can just go to town, right? What's the transfer function between the reference input R and the output Y? I don't know, that's not the cheer. I just know the cheer for G and H. Okay, modify it a little bit, but just say G. Now G is really G bar, right? G bar is this cascade combination of G1 and G. Now it's G over 1 plus GH. H is 1, but now G is G sub C, or actually G sub 1 times G. So our transfer function is G1G over 1 plus G1G. Problem solved. And we can plug in, if we want, for those particular parameterized versions of G1 and G. If we do that, T of S now becomes K over S plus alpha, 1 over S plus 1, over 1 plus K over S plus alpha, 1 over S plus 1. And now you're going, well, that looks like a mess. We have a ratio of ratios, and then we have a 1 down there. But one strategy that is typically helpful is to go ahead and just say, you know what, I can rewrite 1 as, how would I want to rewrite 1 in this case? I'm really just trying to get a common denominator. And the denominator right now in both the numerator and the denominator is that, so why don't I just write 1 as the ratio of that denominator to itself. And if I do that, now the denominator and the numerator goes away, the denominator and the denominator goes away, and I'm left with the transfer function that I want, which is simply K over S plus alpha, S plus 1. That came about from the 1 plus K. Boy, I'm having trouble with K. Questions on that? There's our transfer function between the reference input R and the output Y. What do we want? We want to find the sensitivity of that transfer function with respect to alpha. Can we find that expression? And we will do that two different ways. The first way is we're going to apply the chain rule from calculus. We're going to find the sensitivity of T with respect to G1 and then multiply that by the sensitivity of G1 with respect to alpha. Because we have the transfer function as a function of G1 and we have G1 as a function of alpha, let's just use those pieces separately and put them together to find the overall sensitivity. Let's now start with the sensitivity of T with respect to G1. Do you remember what that was? It's all relative. So we normalize those with T and G1. And now the G1 goes in the numerator, the T stays in the denominator. Now we need to find the partial of T with respect to G1. And the partial of T with respect to G1 is just going to be the partial with respect to G1 of that transfer function that we just derived, G1G over 1 plus G1G. So now we just differentiate that with respect to G1. And we can use the quotient rule or whatever, however you want to do it, to find the partial of that ratio with respect to G1. Here we can say, well, it's going to be the partial of the numerator with respect to G1, which is G, times the denominator, minus the numerator times the partial of the denominator with respect to G1, which is G, all over the denominator squared. But I hope you can see that that numerator simplifies considerably. We have a plus G1GG minus a G1GG. Those go away and we're just left with G in the numerator. We now know that the partial of t with respect to G1 as an expression is just G over 1 plus G1G squared. That's just a piece of the sensitivity of t with respect to G1. The sensitivity of t with respect to G1 is now G1 over t times the partial of t with respect to G1. And that we just found. G1 is just G1, but t was G1G over 1 plus G1G times G over 1 plus G1G squared. And you never thought calculus and algebra could be so fun or so meaningful. Now what can we do? Well, now we can simplify this, that G and G1, and this one of those gets canceled, and we're left with the sensitivity of t with respect to G1. It all collapses to 1 plus G1G. That's part one. We're doing the chain rule. Now we need to do the second piece of that two-piece chain rule computation, and this is now finding the sensitivity of G1 with respect to alpha. And G1, that was our controller that looked like K over S plus alpha. And the sensitivity of G1 with respect to alpha, that has the same structural form as before, partial of G1 over partial of alpha over alpha. Or alpha over G1, partial of G1 with respect to alpha. And now we need to compute this. But we have the expression for G1 in terms of alpha. So now the partial of G1 with respect to alpha is the partial with respect to alpha of K over S plus alpha. What's the derivative of the numerator with respect to alpha? I'm getting impatient. 0, right? And now we subtract the numerator times the derivative or the partial of the denominator with respect to alpha. If I differentiate S plus alpha by alpha, what do I end up with? S doesn't have any alpha in it. We just have alpha, so that's just a 1, and we divide that by S plus alpha squared. So that this partial of G1 with respect to alpha becomes minus K over S plus alpha squared. But that's just the main piece of the second piece of the whole problem. So we need to complete the second part, which is the sensitivity of G1 with respect to alpha. That was alpha over G1, and G1 was K over S plus alpha times minus K over S plus alpha squared. K's cancel. One of those S plus alpha factors cancel, and we're left with minus alpha over S plus alpha for the sensitivity of G1 with respect to alpha. Or we're now almost finished. We have the sensitivity of t with respect to alpha as a chain rule. That was the sensitivity of t with respect to G1 times the sensitivity of G1 with respect to alpha. Sensitivity of t with respect to G1, that was 1 over 1 plus G1G. Sensitivity of G1 with respect to alpha is minus alpha over S plus alpha. And G1G was that. You plug that in for G1G, multiply through by the S plus alpha in the denominator. You're way ahead of me. S of t with respect to alpha is minus alpha S plus 1 over S plus alpha S plus 1 plus k. That's the sensitivity of the transfer function, the closed loop transfer function with respect to alpha. Alpha was the pole in our controller. If we fix alpha at some value, you could now sketch and fix k, the gain in our controller, you could sketch the Bode plot of that sensitivity and see how does alpha, the choice of alpha, how is that influenced, or how is it relative to a frequency variation or as a function of frequency. We'll do that in just a minute, but I want to provide you with one more way of doing this, another way to check your work by means of another sensitivity function or expression. And if you don't get interrupted by the emergency signal, you can be reading page 235 in your textbook. But this is now the sensitivity of t with respect to alpha. We can write as sensitivity natural log of t over the partial of natural log of alpha. But t is usually a numerator over a denominator. So this now we can play with the power of logarithms and products or quotients. What happens if we now take the log of a quotient? That's subtracting the logs. So that now we can rewrite that as the partial of natural log of n over partial natural log of alpha minus partial natural log of d over partial natural log of alpha. But what's that first piece? That's just by definition the sensitivity of the numerator with respect to alpha. And the second piece is the sensitivity of the denominator with respect to alpha. Actually, I think we're going to stay here and just receive that emergency signal. That's only an hour and a half away. I think you're enjoying this. So, here's what we're doing in that hour and a half. We're going to go back to our transfer function, t of s, which you've already derived. That was k over s plus alpha, s plus 1 plus k. That's just our numerator over our denominator. And compute that now using S sensitivity of t with respect to alpha. What do you see happening when we find the sensitivity of the numerator with respect to alpha? What's the sensitivity of k with respect to alpha? We're going to have to find the partial of n with respect to alpha. What's the partial of k with respect to alpha? 0. right? So we've already simplified this to just finding one sensitivity, effectively, the sensitivity of the denominator with respect to alpha. You should be able to show that that equals exactly what we found before. And for fun, you might just plug in an alpha of 3 and a k of 5, sketch the Bode plot, and see how this sensitivity behaves as a function of frequency. We'll pick up there, and obviously I'm going to have some AC notes at the end of this lecture.